Imagine a cold so profound, it's just a whisper from absolute zero. Not the familiar bite of winter wind, nor the sting of ice. This is a cold born of sheer emptiness, a vacuum so vast and silent, it will fundamentally reshape everything you thought you knew about the cosmos. Right now, the space between stars surrounding our planet hovers at about -454 degrees Fahrenheit, or roughly -270 degrees Celsius. This temperature is just a few degrees above the coldest point physics allows. Scientists measure this cosmic baseline at 2.7 Kelvin, a faint warmth left behind by the fading afterglow of the Big Bang itself. But here's what most people misunderstand. Space isn't cold the way winter air is cold. There's no icy wind, no frozen atmosphere, no chill you could actually feel against your skin. The cold of space is something far stranger. It is the near total absence of matter, energy, and heat across the vast majority of the universe. And when you begin to understand what that really means, the temperature of space stops being just a number on a thermometer. It becomes something far more unsettling. Ask almost anyone how cold space is, and the answer usually comes immediately: freezing. Colder than Antarctica. Close to absolute zero. This response feels obvious because the picture in our mind seems so clear. Space is dark. Space is empty. Of course, it must be unimaginably cold. But that confident answer hides a problem. The question itself is slightly wrong. Not completely wrong, but wrong in a way that quietly misleads us about how the universe actually works. Because when we ask how cold space is, we're imagining space as if it were something like air on a winter night, or water in a frozen lake. We picture a substance that surrounds you and drains the heat from your body. In reality, space is nothing like that. To understand why, we have to start with something simple that we rarely think about: what temperature actually means. When we say something is hot or cold, we're usually describing a sensation. Step outside during a bitter winter storm, and the cold seems to attack you. The air feels sharp. Your breath fogs. Your fingers begin to sting. On an especially brutal day in Antarctica, temperatures can plunge to -28 degrees Fahrenheit, or -89 degrees Celsius, one of the coldest natural temperatures ever recorded on Earth. But even that extreme cold still relies on something essential: air. The atmosphere around you is packed with molecules, mostly nitrogen and oxygen, moving constantly in every direction. At warmer temperatures, those molecules move faster. At colder temperatures, they move slower. Either way, they are still there, colliding with your skin every second. Each collision transfers a tiny amount of energy between your body and the surrounding air. If the air is colder than your body, those collisions slowly steal your heat. Billions upon billions of microscopic impacts carry energy away from you, molecule by molecule, until your body temperature begins to drop. Your nerves interpret that loss of heat as the feeling we call cold. The same thing happens when you touch cold metal. A metal railing sitting outside on a winter night might also be around -4 degrees Fahrenheit, or -20 degrees Celsius. When your hand touches it, heat rushes out of your skin into the metal through conduction. The faster that energy flows away from your body, the colder the object feels. But notice something important about every example of cold we experience on Earth. Air molecules collide with you. Water molecules surround you. Metal atoms press against your skin. Cold always involves matter carrying heat away. That assumption is built so deeply into human experience that we almost never question it. We imagine cold as a kind of invisible substance that fills the environment, like a freezing fog waiting to surround us. Space does not work that way. In the deep vacuum between stars, there is almost no matter at all. A single cubic centimeter of air at sea level contains around 25 billion molecules. Every breath you take pulls in a swarm of particles so large that the number is difficult to even picture. Now imagine removing almost all of them. In the vast regions between stars, that same cubic centimeter of space might contain one atom, sometimes fewer. That means the density of matter in interstellar space is so low that particles rarely collide with anything. A lonely hydrogen atom might travel for miles, or even kilometers, before encountering another particle. There is simply nothing there to touch you. No molecule striking your skin, no fluid carrying heat away, no medium surrounding your body at all. Which leads to a strange conclusion. If you could somehow float in deep space without a suit, ignoring the many other deadly consequences of vacuum, you would not immediately feel the kind of cold we associate with winter. There would be no icy wind biting your face, no frozen air pulling warmth from your skin. At first, the environment around you would feel strangely neutral, almost like standing in perfect stillness. But that neutrality is deceptive. Because although space cannot steal heat through contact, your body would still be losing energy in another way, through radiation. Every object in the universe that has a temperature above absolute zero emits energy in the form of electromagnetic radiation. Warm objects glow mostly in infrared light, invisible to our eyes, but constantly streaming outward. Your body is doing this right now. Even sitting comfortably indoors, you're quietly radiating heat into the room around you. The walls radiate energy back. The air transfers warmth through convection. Everything reaches a balance. But in space, that balance disappears. The heat you radiate simply leaves. It travels outward as infrared photons, moving away at the speed of light into the darkness. And unless another source of radiation replaces that energy, like sunlight, your body slowly cools. Not because space is actively freezing you, but because the universe is giving nothing back. This is why the temperature of space is such a strange concept. If you placed a thermometer floating alone, far from any star or planet, it would not measure the temperature of space itself. Instead, it would measure the balance between the radiation it absorbs and the radiation it emits. Space itself is not a substance with a temperature. It is a stage where objects gain or lose heat depending on the light around them. Near the Sun, radiation pours across the solar system. At Earth's orbit, sunlight delivers about 1,360 watts of energy per square meter, enough to warm surfaces to well above the boiling point of water if they cannot cool themselves. A surface exposed directly to sunlight in orbit can reach temperatures above 250 degrees Fahrenheit, or about 120 degrees Celsius, hotter than most household ovens. But step into shadow, and the situation changes immediately. Without sunlight, objects radiate heat into the void and cool rapidly. Temperatures can fall to around minus 250 degrees Fahrenheit, or minus 157 degrees Celsius, in deep shadow. The difference between those two environments can exist just inches apart. This is why spacecraft are built with elaborate thermal control systems. Engineers carefully design reflective surfaces, insulation layers, heaters, and radiators to manage the constant battle between heating and cooling. Without those systems, spacecraft would swing violently between extremes. Parts facing the sun would overheat. Parts facing darkness would freeze. The moon provides a dramatic example of this effect. Unlike Earth, the moon has almost no atmosphere. There is no air to distribute heat across its surface. As a result, the lunar environment experiences enormous temperature swings. During the long lunar day, when sunlight shines directly on the surface, temperatures can climb to around 260 degrees Fahrenheit, hot enough to boil water. But during the equally long lunar night, when the sun disappears for roughly 2 weeks, the surface cools dramatically. Temperatures plunge to around minus 280 degrees Fahrenheit, or minus 73 degrees Celsius. That is a swing of more than 540 degrees Fahrenheit, or 300 degrees Celsius, on the same piece of ground. And it happens simply because there is no atmosphere to hold heat. But even these extreme temperatures are not really the temperature of space. They are the temperatures of objects within space, the rocks, the dust, the spacecraft, the astronauts. Space itself remains almost empty. Which brings us back to the number scientists often quote when describing the cold of the universe. If an object drifts through deep interstellar space, far away from stars or galaxies, it will eventually cool until it reaches equilibrium with the faint background radiation that fills the cosmos. That equilibrium temperature is about -454 degrees Fahrenheit, or -270 degrees Celsius, just a few degrees above absolute zero. That faint glow is known as the cosmic microwave background, the leftover heat from the Big Bang itself. It fills every corner of the universe like a dim thermal whisper, the oldest light still traveling through space. This ancient radiation sets the ultimate baseline temperature of the cosmos. It's not exactly the temperature of space itself, but it is the temperature any lonely object drifting through the void will eventually reach. And when you compare that number to anything we experience on Earth, the scale becomes almost impossible to grasp. The coldest natural temperature ever measured on our planet, -28 degrees Fahrenheit or -89 degrees Celsius, suddenly seems almost warm. Liquid nitrogen, used in laboratories to freeze biological samples, boils at -320 degrees Fahrenheit, or -96 degrees Celsius. Even that is far warmer than the natural background temperature of the universe. Space is colder still. But the most unsettling part of this story is not the number itself. It is what the number represents. Because when you look across the universe, you begin to realize that this near-absolute cold is not the exception. It is the rule. To understand how cold space truly is, we need to step back and look at something even stranger than empty vacuum. The entire universe is glowing, not brightly, not in visible light, but in an extremely faint, ancient glow that fills every direction of space. It's like the dying embers of a fire that burned billions of years ago. This glow is called the cosmic microwave background, and it is the reason scientists say the temperature of the universe is about -454 degrees Fahrenheit, or -270 degrees Celsius. But that number isn't random. It is the leftover heat from the moment the universe itself began, around 13.8 billion years ago. The universe was not cold at all in its infancy. It was unimaginably hot. In the first moments after the Big Bang, the temperature was far beyond anything we can recreate in laboratories today. Matter and energy existed in a searing plasma, hotter than the core of any star. At those temperatures, atoms could not exist. Electrons and protons moved freely through space, like sparks in a cosmic furnace. Light itself could barely travel. Photons constantly slammed into charged particles, scattering in every direction. The universe was not dark, it was a blinding, glowing fog where light could not move more than a tiny distance before colliding with something. For hundreds of thousands of years, the cosmos remained in this state. But as space expanded, something important happened, the universe began to cool. Expansion spreads energy across larger and larger volumes. Imagine stretching a glowing piece of metal while it radiates heat, the same amount of energy becomes distributed across a greater area, lowering the temperature. The early universe behaved in a similar way. As space expanded, the temperature slowly dropped. Eventually, about 380,000 years after the Big Bang, the universe cooled enough for atoms to form for the first time. Electrons were finally able to attach themselves to protons, creating neutral hydrogen atoms. When that happened, something remarkable occurred. Light was suddenly free. Without free electrons scattering photons in every direction, radiation could finally travel across the universe without constant collisions. The cosmic fog cleared almost instantly. For the first time in cosmic history, the universe became transparent. The photons released at that moment began a journey that continues even today. They streamed outward in every direction, carrying with them a snapshot of what the universe looked like when it was less than 1% of its current age. At the time, the temperature of the universe was about 5,000 degrees Fahrenheit, or roughly 2,700 degrees Celsius, hot enough that the entire sky would have glowed with a deep reddish light, like the interior of a giant furnace. But the universe did not stop expanding. Over billions of years, space stretched farther and farther. As it did, the light traveling through it stretched as well. Its wavelength grew longer. Its energy decreased. That same radiation that once glowed red-hot gradually cooled. First, it shifted from visible light into infrared, then into microwaves. And today, after nearly 14 billion years of cosmic expansion, those ancient photons have cooled to just 2.7 Kelvin, which corresponds to -454 degrees Fahrenheit, or -270 degrees Celsius. This faint microwave glow fills the entire universe. It surrounds every galaxy, every star, every planet. It is the oldest light we can observe, the thermal fossil of the Big Bang itself. For most of human history, no one knew it existed. The discovery happened almost by accident in 1964. Two radio astronomers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna in New Jersey, designed to detect faint radio signals from space. But every time they turned on the instrument, they encountered an annoying background noise, a faint, constant hiss. They checked everything: electronic interference, equipment errors, even pigeon droppings inside the antenna. Nothing explained the signal. No matter where they pointed the antenna, the hiss remained. It came equally from every direction. Eventually, they realized the signal was not coming from Earth at all. It was coming from the universe itself. They had discovered the cosmic microwave background. The temperature they measured corresponded to about -454 degrees Fahrenheit, nearly identical in every direction across the sky. Later satellites would measure this radiation with extraordinary precision. Missions like COBE, WMAP, and Planck mapped the entire sky, confirming that this faint microwave glow fills the cosmos almost perfectly uniformly. It is the most perfect example of a thermal spectrum ever observed in nature. But more importantly, it establishes the baseline temperature of the universe. Any object drifting alone in deep space, far away from stars or galaxies, will eventually cool until it reaches equilibrium with this background radiation. At that point, it stops cooling. Its temperature settles at around -454 degrees Fahrenheit, or -270 degrees Celsius. That is the closest thing the universe has to a default temperature. To appreciate just how extreme this is, consider some familiar benchmarks. Liquid nitrogen, commonly used in laboratories to freeze materials instantly, boils at -320 degrees Fahrenheit. Liquid helium, one of the coldest substances used in cryogenic experiments, boils at -452 degrees Fahrenheit. Even that is slightly warmer than the cosmic background. In fact, the universe itself is colder than most cryogenic liquids used by scientists on Earth. And yet, this near-absolute cold fills almost every cubic meter of space. If you could travel far away from any star, far beyond the outer edges of galaxies, into the enormous voids between clusters of galaxies, the environment around you would be almost perfectly uniform. No sunlight, no starlight strong enough to warm anything. Just the faint microwave glow of ancient radiation, keeping the universe barely above absolute zero at -454 degrees Fahrenheit. It is the quietest thermal state the cosmos can naturally reach. But that raises a deeper question. If the universe naturally settles into such extreme cold, why does any warmth exist at all? Why are there stars burning at millions of degrees? Why are there planets warm enough for oceans? Why is Earth comfortably sitting around 59 degrees Fahrenheit, or 15 degrees Celsius, instead of frozen solid? The answer lies in a few extraordinary exceptions scattered across the darkness. Tiny islands of heat in a vast ocean of cold. And those islands are created by the most powerful furnaces in the universe, stars. If the universe naturally settles toward -454 degrees Fahrenheit, then the warmth we experience on Earth needs an explanation. Because that warmth is not the rule, it is the exception. Across the universe, almost every place you could possibly travel sits close to that same cosmic baseline temperature. Yet scattered through this enormous darkness are objects that burn with unimaginable heat. A star is essentially a gigantic sphere of gas collapsing under its own gravity. As the gas compresses, the pressure in the center becomes so intense that atomic nuclei begin to fuse together. Hydrogen atoms collide and merge into helium, releasing enormous amounts of energy in the process. That energy pours outward in the form of light and heat. Our own Sun, for example, has a surface temperature of about 9,900 degrees Fahrenheit. That already places it on a completely different scale compared to the background temperature of space. But the Sun's core is far hotter still. Deep in its center, where the pressure from the Sun's enormous mass squeezes hydrogen atoms together, temperatures climb to about 27 million degrees F. Those conditions allow nuclear fusion to occur continuously, producing the energy that keeps the Sun shining. Every second, the Sun converts roughly 4 million tons of matter into pure energy. That energy streams outward in every direction, crossing the emptiness of space until a tiny fraction of it reaches Earth. After traveling 93 million miles, sunlight warms our planet. Without it, Earth would not be a blue world with oceans and clouds. It would be a frozen sphere drifting through space. If the Sun suddenly disappeared, our planet's temperature would begin to fall rapidly. Within weeks, average surface temperatures would drop below -100 degrees Fahrenheit. Within a year, Earth would cool to roughly -50 degrees Fahrenheit. Eventually, over thousands of years, the planet would approach the background temperature of the universe itself, settling near -454 degrees Fahrenheit. The warmth of our world exists entirely because we orbit close to a star. And our Sun is not particularly extreme. Across the galaxy, stars come in many different sizes and temperatures. Some burn hotter than anything we can easily imagine. Blue supergiant stars, for example, can have surface temperatures exceeding 20,000 degrees Fahrenheit. Their intense radiation floods surrounding space with energy, lighting up vast clouds of gas called nebulae. In the most massive stars, the cores can reach hundreds of millions of degrees as heavier elements fuse together in layers, like the interior of a cosmic furnace. But even these incredible objects share an important characteristic: they are tiny compared to the space between them. Imagine shrinking the Sun down to the size of a ping-pong ball. At that scale, the nearest star would be another ping-pong ball sitting roughly 700 meters away. Between those two tiny spheres would stretch hundreds of miles of completely empty darkness. That enormous distance is filled with almost nothing. The few atoms drifting there absorb almost no heat. They rarely collide. They barely interact with anything at all. In other words, the warmth produced by stars spreads across space, but it fades incredibly quickly. Light obeys something called the inverse square law. When radiation spreads outward from a source, its intensity decreases with the square of the distance. Double the distance from a star, and the energy you receive drops to 1/4. Triple the distance, and it drops to 1/9. By the time sunlight reaches Pluto, more than 3.7 billion miles from the Sun, the energy it receives is so weak that surface temperatures hover around -375 degrees Fahrenheit. Even within our own solar system, the dominance of cosmic cold becomes obvious the farther you travel from the Sun. Mercury, the closest planet to the Sun, experiences scorching daytime temperatures of around 800 degrees Fahrenheit. But on the side facing away from the Sun, where there is no atmosphere to hold heat, temperatures plunge to -290 degrees Fahrenheit. The Moon experiences similar extremes. Under direct sunlight, its surface reaches about 260 degrees Fahrenheit, but during lunar night, temperatures fall to around -280 degrees Fahrenheit. All of this happens because there is no atmosphere to distribute heat. In space, sunlight warms only the surfaces it touches. Everything else cools rapidly. Spacecraft designers know this problem well. Satellites orbiting Earth must constantly manage the delicate balance between heating and cooling. Parts exposed to sunlight can climb above 250 degrees Fahrenheit, while shaded components may drop below -250 degrees Fahrenheit. These enormous temperature differences can exist on the same spacecraft at the same time. The reason is simple: space does not regulate temperature. It does not mix warm air with cool air the way Earth's atmosphere does. It does not distribute heat through wind or water currents. It simply allows energy to escape. Which means every object floating through space must find its own thermal balance between radiation coming in and radiation going out. For planets, that balance determines whether they become icy wastelands, scorching deserts, or something far rarer, a narrow band of temperatures where liquid water can exist. Earth's average surface temperature sits around 59 degrees Fahrenheit. That number might seem ordinary to us, but on the scale of the universe, it is astonishing. It exists only because our planet occupies a very specific distance from the sun. Too close, and the oceans would evaporate. Too far, and they would freeze solid. Astronomers call this narrow region the habitable zone. In our solar system, it forms a thin ring around the sun where temperatures allow water to remain liquid on a planet's surface. But compared to the distances between stars, that zone is incredibly small. It is like a tiny oasis in an enormous desert. Which leads to a realization that becomes harder to ignore the more you examine the universe. Stars generate enormous heat, but the space between them is so vast that their warmth barely touches most of the cosmos. Even inside galaxies, the majority of space remains extremely cold. The light from stars illuminates the darkness, but it does not fill it. And when we begin to measure how much of the universe actually contains heat compared to how much remains near -454 degrees Fahrenheit, the scale of that imbalance becomes truly staggering. Once you begin to look at the universe on larger scales, something unsettling starts to become clear, and it changes the way you see everything that felt familiar before. The heat from stars feels powerful to us, but only because we happen to live next to one. The sun dominates our sky. It lights our days. It drives our climate. And it keeps Earth comfortably near 59 degrees Fahrenheit, creating conditions that feel normal to us, but are anything but normal when compared to the rest of the universe. Because the moment you step back and look at the true scale of the cosmos, that warmth begins to shrink. Not gradually, but dramatically, until it becomes almost insignificant. Stars may burn with incredible intensity, reaching temperatures of thousands or even millions of degrees, but they occupy almost none of the universe. To understand this, imagine standing inside a vast, empty cathedral. A structure so enormous that its walls stretch beyond your vision and its ceiling disappears into darkness far above you. Now imagine releasing a handful of glowing fireflies into that space. They shine brightly. Their light is real. Their presence is undeniable. But the space around them remains overwhelmingly dark. That is what the universe is like. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. A number so large it feels almost impossible to comprehend. And yet, those stars are spread across a disk that is about 100,000 light-years wide and roughly 1,000 light-years thick. Even inside a galaxy filled with hundreds of billions of suns, the stars are separated by distances so vast that they almost never interact with one another directly. In our region of the galaxy, the average distance between stars is about 4 light-years, which is more than 24 trillion miles. A gap so large that if you tried to travel it with current technology, it would take tens of thousands of years. To make this easier to visualize, imagine shrinking the sun down to the size of a grain of sand. At that scale, the nearest star would be another grain of sand sitting more than a mile away. And everything between those two grains would be completely empty. No light sources nearby, no heat, just space. And this is not an unusual arrangement. This is the standard spacing of stars throughout much of our galaxy. But when you step beyond the scale of galaxies, the emptiness becomes even more extreme. Galaxies themselves are separated by distances that make the space between stars look almost crowded by comparison. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. Which means the light you see from it tonight began its journey long before modern humans existed, long before civilization, long before recorded history. Between galaxies lies intergalactic space, a region where matter becomes even more scarce, where the density drops so low that in some areas there may be only one particle in an entire cubic meter of space. That particle might drift for millions of miles without ever encountering another. In such an environment, heat has no effective way to move or spread. Even if those particles are moving quickly, even if their motion corresponds to extremely high temperatures, in a technical sense, there are simply too few of them to carry meaningful amounts of energy. It is like trying to warm an entire building using a handful of sparks floating in the air. There's not enough substance to transfer heat. And when astronomers map the universe on its larger scales, they discover something even more striking. Galaxies are not evenly scattered. Instead, they form enormous filaments stretching across space like threads in a vast cosmic web. And where those filaments intersect, galaxy clusters form, dense regions containing hundreds or even thousands of galaxies bound together by gravity. But between these structures lie vast regions known as cosmic voids. These voids are among the largest structures in existence, spanning hundreds of millions of light-years across. And inside them, galaxies are extremely rare. A spacecraft traveling through one of these regions could move for tens of millions of light-years without encountering a single galaxy, without seeing any significant source of light or heat. Only darkness and the faint background glow of the universe itself. In these regions, the temperature settles close to -454 degrees Fahrenheit, almost perfectly uniform, almost completely unchanged across enormous distances. Astronomers estimate that these cosmic voids make up roughly 80 to 90% of the total volume of the observable universe. Which means that if you could randomly place yourself anywhere in the cosmos, the overwhelming probability is that you would find yourself in one of these vast, cold, empty regions, not near a star, not near a galaxy, but drifting in darkness, surrounded by space sitting near -454 degrees Fahrenheit. Even inside galaxies where stars exist, most of the volume is still empty. Between stars lies the interstellar medium, a thin gas composed mostly of hydrogen, but it is incredibly sparse, often containing only a few atoms per cubic centimeter, which is trillions of times less dense than the air you are breathing right now. Those atoms can have very high temperatures, sometimes reaching thousands or even millions of degrees in terms of their motion. But that does not mean the space feels warm. Because temperature measures how fast particles move, not how much energy is actually present in a given volume. A single fast-moving particle can correspond to a very high temperature, but it still carries almost no total energy. A room filled with air at 68 degrees Fahrenheit contains vastly more thermal energy than an enormous region of space filled with only a few scattered particles, even if those particles are technically hot. So even when space is described as having regions of high temperature, those regions are effectively still cold in any practical sense because there is almost nothing there to transfer that energy. This is the key idea. The universe can contain extremely hot objects like stars burning at thousands of degrees or gas heated to millions, and still remain overwhelmingly cold overall. Because those hot objects are small, and the empty space between them is vast. When scientists attempt to estimate how much of the universe is actually occupied by stars, the result becomes almost impossible to grasp. The observable universe is unimaginably large, containing volumes so vast that the numbers used to describe them stretch far beyond intuitive understanding. But when you compare that volume to the total volume of all stars combined, the fraction becomes so small that it is effectively zero. Not figuratively, but almost literally. If you rounded the fraction of space occupied by stars down to zero, you would barely change any meaningful calculation about the universe. Almost everything else is empty. An empty space naturally drifts toward a single temperature, -454 degrees Fahrenheit. This is the true background of the cosmos. Not blazing stars, not glowing galaxies, but cold, silent emptiness stretching across distances so vast that even light takes millions of years to cross them. The bright points we see in the night sky are real, and they are powerful, but they are not the main story. They are the exceptions. Tiny islands of heat in an ocean of cold. Once you begin to understand how overwhelmingly cold the universe is across space, another realization slowly starts to emerge. And this one is even more unsettling because it extends beyond distance and into time itself. The warmth we experience on Earth is not just rare in space. It is rare in time. Right now, we exist during a very specific chapter in the history of the universe. A period when stars are still forming, still burning, and still filling the sky with light. And this period is known as the stelliferous era, the age of stars. It feels permanent. It feels stable. It feels like the natural state of things, but it is not. Stars are powerful, but they are temporary. And every star you see in the night sky is slowly using up its fuel, converting hydrogen into helium through nuclear fusion, releasing enormous amounts of energy in the process. But that process cannot continue forever. Fuel runs out, and when it does, the star changes. Our own Sun is a perfect example because it has a total stable lifetime of about 10 billion years. It formed roughly 4.6 billion years ago, which means it is already about halfway through its life. For now, it provides a steady and reliable source of energy, keeping Earth warm enough to maintain oceans, weather systems, and life, holding the average surface temperature near 59 degrees Fahrenheit. But that balance will not last. Over time, the Sun is slowly becoming brighter. And as hydrogen in its core is converted into helium, the internal structure of the star changes, increasing the rate of fusion and gradually raising its energy output. In about 1 billion years, the Sun will be about 10% brighter than it is today. And that may not sound dramatic, but for Earth, it is enough to begin a chain reaction. More sunlight means more heat. More heat means more water evaporating into the atmosphere. And water vapor is a powerful greenhouse gas. So the extra vapor traps more heat, which leads to more evaporation, which leads to even more warming. Eventually, this feedback loop pushes the planet into a runaway greenhouse state where the oceans begin to boil away, clouds thicken, and surface temperatures rise far beyond anything life could survive. The stable climate that keeps Earth near 59 degrees Fahrenheit disappears long before the Sun itself reaches the end of its life. And then, billions of years later, the transformation becomes even more dramatic. After roughly 5 billion years, the Sun will exhaust the hydrogen in its core. And without that fuel, the balance between gravity and internal pressure collapses, causing the core to contract while the outer layers expand. The Sun becomes a red giant, its outer atmosphere swelling outward, possibly extending beyond the orbit of Venus and maybe even reaching Earth itself. During this phase, the surface of the Sun will actually be cooler than it is today. But its enormous size will make it vastly more luminous, flooding the inner solar system with energy. Any remaining traces of oceans or atmosphere on Earth would be stripped away or burned off, and temperatures would climb far beyond anything we experience today. Even if Earth somehow avoided being swallowed, it would no longer be a habitable world. Eventually, the Sun will shed its outer layers into space, creating a glowing shell of gas, while its core remains behind as a white dwarf, a dense, compact remnant roughly the size of Earth. At first, that remnant will still be extremely hot, with surface temperatures exceeding 180,000 degrees F. But it will no longer produce energy through fusion. And instead, it will simply cool slowly, steadily, and without interruption. Over billions and trillions of years, it will radiate away its remaining heat into the surrounding vacuum, growing dimmer and colder, approaching the cosmic background temperature of -454 degrees Fahrenheit. This process is not unique to our Sun. It is happening, or will happen, to almost every star in the universe. Massive stars burn through their fuel quickly, living fast and dying in violent explosions called supernovae, while smaller stars burn more slowly, lasting billions or even trillions of years. The smallest stars of all, known as red dwarfs, are incredibly efficient. And some of them may shine for 10 trillion years or more, far longer than the current age of the universe. But even they will not last forever. Eventually, every star will run out of fuel. And when that happens, the universe will begin to grow darker. Star formation itself is already slowing down because galaxies are gradually using up the gas needed to create new stars. And as that gas is consumed or dispersed, fewer and fewer new stars will form. The universe is not becoming brighter over time. It is becoming dimmer. After roughly 100 trillion years, the era of stars will effectively come to an end. As the last red dwarfs finally exhaust their fuel and no new stars take their place, the universe then enters a new phase, often called the degenerate era, where the dominant objects are no longer shining stars, but the cold remnants left behind, white dwarfs, neutron stars, and black holes. At first, some of these remnants still contain heat, but none of them generate new energy, and they simply continue cooling. White dwarfs fade, neutron stars lose their heat, and even black holes, the most extreme objects in the universe, do not last forever. Through a process known as Hawking radiation, black holes slowly lose mass and energy over incredibly long timescales, with a black hole the mass of our Sun taking around 10 to the power of 67 years to evaporate. While a supermassive black hole could take 10 to the power of 100 years or more. These numbers are so large that they stretch beyond meaningful human understanding. And throughout all of this time, the universe continues to expand. And as space grows larger, the remaining energy within it becomes more diluted. The cosmic microwave background, which currently maintains a temperature of -454 degrees Fahrenheit, continues to cool, its radiation stretching to longer wavelengths and lower energies. While the faint glow of the Big Bang slowly fades, the universe grows darker and colder. In that distant future, trillions upon trillions of years from now, the cosmos approaches a state where almost no concentrated energy remains anywhere. With no stars, no bright galaxies, only scattered particles and fading radiation drifting through an ever-expanding void, temperatures everywhere inch closer and closer to absolute zero. And when viewed on this scale, the present moment becomes something extraordinary. Because the warmth we experience, the stable temperature near 59 degrees Fahrenheit, the existence of sunlight, oceans, and a living biosphere, all of it exists during a brief window in cosmic history. A window that will eventually close. The age of warmth is not permanent. It is a phase, a temporary condition in a universe that is steadily and inevitably moving toward cold. When you bring all of this together, when you hold the scale of space and the scale of time in your mind at the same moment, a clear and unsettling picture of the universe begins to form. And it is very different from the one most people imagine. The universe began in unimaginable heat, a state so extreme that matter itself could barely exist, where energy and particles collided in a dense, blinding plasma, hotter than the core of any star alive today. But that state did not last. For 13.8 billion years, the universe has been expanding. And as space expands, the energy within it spreads out, becoming thinner, weaker, and colder, like embers from a fire drifting apart until their glow fades into darkness. Today, the faint afterglow of that original fire still fills the universe, maintaining a baseline temperature of about -454 degrees Fahrenheit. And this is the closest thing the cosmos has to a natural resting point. And almost everywhere you look, that is exactly where the temperature is. The stars we see in the night sky feel dominant to us because they are bright, because they are close, and because our entire existence depends on one of them. But when you measure the universe honestly, stars are incredibly rare. They are not the background. They are the exception. Imagine the entire observable universe as an ocean. Not an ocean of water, but an ocean of darkness stretching across tens of billions of light years. And scattered within that ocean are tiny sparks of light, stars and galaxies burning with nuclear fire. Those sparks are real. They are powerful, but they occupy almost none of the total volume. They are like scattered embers floating on a frozen sea. Small, isolated, and surrounded by overwhelming cold. If you could travel far beyond our galaxy, far beyond the Milky Way, beyond the clusters and filaments that make up the visible structure of the universe, and into one of the enormous cosmic voids, you would eventually find yourself in a region where the sky is almost completely black. No nearby stars, no bright galaxies, no meaningful sources of heat, only darkness and the faint uniform glow of ancient radiation, maintaining the temperature near -454 degrees Fahrenheit. You could drift through that emptiness for millions of years without encountering anything significant. No light, no warmth, no change. Just a vast, silent environment where the universe has settled into its natural state. And that state is cold. Even the regions that contain galaxies do not escape this reality. Because galaxies themselves are mostly empty, filled with enormous distances between stars, where space behaves almost exactly like the void beyond them. The warmth we associate with the universe, the light we see, the heat we feel, all of it comes from a tiny fraction of matter compressed into stars scattered across distances so large that their influence fades almost immediately outside their local surroundings. Which means that the true character of the universe is not warmth. It is cold. And not just in space, but in time. Because the era we live in, the age of stars, is only a brief chapter in the history of the cosmos. And it will not last forever. Stars will burn out, galaxies will grow dark, the cosmic microwave background will continue to cool, and the universe will move closer and closer to a state where almost no usable energy remains anywhere. A state of maximum stillness, maximum emptiness, and near absolute cold. But here is where the perspective shifts. Because within this vast, cold universe, something extraordinary has happened. On one small planet orbiting one ordinary star at just the right distance, conditions exist that are almost impossible to find anywhere else. On Earth, the surface temperature sits near 59 degrees Fahrenheit, a narrow range that allows water to remain liquid, that allows chemistry to become complex, that allows life to exist. This is not the default state of the universe. It is an exception, a rare balance of conditions that depends on a chain of events stretching back billions of years, from the formation of our star, to the position of our planet, to the structure of our atmosphere, to the stability of our climate. Change any one of those factors, and Earth would no longer be warm. It would resemble Mars, where temperatures sit near -80 degrees Fahrenheit, or Venus, where runaway heating drive temperatures above 860 degrees Fahrenheit. Instead, we exist in a narrow band, a thin layer of warmth surrounded by a universe that is almost entirely cold. And when you compare those two realities, the vast cold of space and the fragile warmth of our world, the contrast becomes difficult to ignore. The terrifying truth about how cold space really is not just the number -454 degrees Fahrenheit. Although that number is extreme enough on its own, it is the proportion. Almost every place that exists in the universe is colder than anything humans have ever experienced on Earth. And almost every moment in the future of the universe will be colder than the present. Warmth, the condition that makes oceans possible, that makes weather possible, that makes life possible, exists only in small, isolated regions around individual stars for limited periods of time. Tiny pockets of heat surrounded by an ocean of cold. And yet, within one of those pockets, on this small world, at this moment in cosmic history, the temperature happens to be just right. Warm enough for oceans, warm enough for life, warm enough for us to look out into the universe and ask these questions. Out there, the cosmos remains silent, dark, and unimaginably cold, hovering near -454 degrees Fahrenheit in every direction. But here, at least for now, it is warm, comfortable. And the chilling reality is that over 99.9999999% of the entire universe is utterly devoid of warmth.